Okay, so graphing is something that does appear on your homework number 2. It does appear in your labs as well, so it's really good to be able to interpret a graph properly. And I think what I'd like to do is to not make it too abstract. I just want to start by doing an example, and we'll learn about it as we go. So I'm going to go ahead and put down a graph of position versus time. Notice that's how you say it. Whatever is on the vertical axis is first versus whatever is on the horizontal axis. So this is an x versus t graph. X is going to be measured in meters. Time is going to be measured in seconds. If you put the units there on the side, then you don't have to put every single thing that you label, every single tick mark with one. And so the reason I'm switching back to position is, of course, because displacement is something you do, right? So displacement is something you do over the course of some amount of time. If you want to index where you are at any given time, then we go back to position. Okay, so position is something at such and such a time I have this position, whereas displacement is something you do from one time to another time. Okay, so let me go ahead and just make a graph. Let me mark out 1, 2, 3, 4 seconds on the t-axis. And then let me label, I guess, up to 1, 2, 3. So plus 1, plus 2, plus 3 meters of position. I didn't mark off any negative x values, so apparently I'm preparing for something that's only going to be moving, or only going to be to the right of the origin, but that's okay. And then I'm just going to throw down a shape. And it doesn't really matter what the shape is, as long as once you have the shape there, then you know what that would indicate in the real world. So let's go ahead and do that. I'll start off at 0, 0. Go up to 3 meters after 1 second. Go back down to 2 meters at 2 seconds, and then 2 meters still at 4 seconds. So those are my 4 points, and I'm going to suppose that, just for the sake of discussion, I'll connect them with straight lines like this. So that's going to be my graph that I analyze and wring as much information out of it as possible. Before I start seeing what other more subtle forms of information I can get out of it, one of the things that I should probably do is draw what I would see with my own eyes if I were watching something undergoing the motion given by this graph. So I'm just going to go ahead and put down a number line. And then draw some object moving according to what this graph says. So according to the graph, when the clock starts, t equals 0, what x value should I draw the object? 0. So here I am at t equals 0 seconds. And then, after 1 second, they're all the way over here at plus 3 meters. So that's your t equals 1 second. I'm all the way over there. Then apparently after 2 seconds, I come back a little bit. So this is 2 seconds. And then I apparently like it there because that's where the rest of the motion is the person sitting at plus 2 meters. So essentially, what we have is the person goes to the right, comes back to the left, and then just sits there. That's the motion. That's the motion being given to us by this graph. Well, that's raw information handed to us on a silver platter, but there is even more information that can be wrung out of this graph. One of the things that you can do is take the slope. So this is, again, where your mathematical training comes in. Let's take the slope. There are 3 distinct slopes on this, so let me label those sections A, B, and C. and let me take the slope of each one. So, for instance, for section A, you take the slope, that's rise over run. I guess let's do it over here. For A, the slope, which is rise over run. Now, the rise is how much you move on the vertical axis. In this case, it's how much you change your x value, because x value is actually plotted on the vertical axis, and what's being plotted on the horizontal axis is actually time. So if we take the slope, we'll get delta x over delta t, which is what? Well, I mean, what does it represent physically? Well, it's average velocity from homework number 1. So if I take the slope between 2 points, it actually gives me the average velocity between those 2 points. So I can actually get velocity information out of the graph as well. When you take the slope of an x versus t graph between 2 points, what you find is the average velocity that you have between those 2 points. Okay, so let's do it here. What's the rise is how much? Plus 3 what? Meters. And what's the run? 1 second. So my average velocity in the first second, this is 0 to 1 seconds, is plus 3 meters per second. But that's not all. Not only is that my average velocity, but I would like to point out to you that if I took the slope on any part of this, it has the same slope. So that means that not only was my velocity on average 3 meters per second, it literally was that the whole time. So because it's a constant slope, it actually tells me that the instantaneous velocity is plus 3 meters per second for that whole time segment. So you would agree that if you took the slope of that whole section or any tiny little part thereof, you would get the exact same slope. So what that tells me is that the velocity is not only that on average, but it happens to be that the whole time. That's, of course, a straight line. That's what a straight line is, right? It has a slope that's the same throughout. It's not a curve. All right, so I've not only been able to find the average velocity for the first second, I actually have complete velocity information for the entire first second. All you did in the first second was go 3 meters per second, every moment. So we can sketch that on here. Your velocity was plus 3 meters per second, plus 3 meters per second, plus 3 meters per second. That's all you did during the first second as you're going to the right. Just move at a constant velocity. All right? Let's keep going. For segment B, if we take the slope, we can find the average velocity from 1 second to 2 seconds. What's the rise there in segment B? Minus 1 what? Meter. And what's the run? 1 second. So my average velocity during this part of the trip was negative 1 meter per second. And again, because it's a constant slope, it's a line, it does not a curve. That was literally the velocity at every point during that part. So I can sketch that here. The velocity was minus 1 meter per second, minus 1 meter per second, etc. That's all I did in the second of the trip, so to speak, from 1 second to 2 seconds. All right, what's the slope of the last part? The 2 to 4 seconds? 0. Rise is 0, so that makes it 0. So for segment C, which is from 2 to 4 seconds, my average slope is 0, and it literally stayed that the whole time, right? Because it's a constant slope. I didn't just average out to going nowhere. I literally went nowhere no point during that trip. So what I could do Oh, I guess I should add that here. So this, of course, when I'm here, when I get here, I go 0 meters per second. I stay there for the remainder of the trip. So what I could do is I could just go ahead and make a whole new graph where I sketch the velocity information. So this graph has not only told me where I am at all times, but because I know where I am at all times, I can deduce velocity information. Let me go ahead and put that below here so I can line up the t-axes. So 0, 1, 2, 3, 4 seconds. And notice here that I do have to make room on both the positive and negative vertical axis because I do have both positive and negative values that I have to plot. I'm plotting the velocity. I guess I should label this, technically I'm plotting the x velocity. Of course there is no other velocity, but we will get there later, so let's have it be correct now. So we have to label up to 1, 2, 3 in this axis, and then only down to -1 on this axis. And let's go ahead and sketch it. So here's what it looks like. The entire first second, I had a constant velocity of +3. Then for the entire second, I had a velocity of -1. And then I had a velocity of 0. Now, this graph, you should be looking at this a little funny and saying, why does it have these weird jump cuts? Well, really, it's a pretty oversimplified. Okay? So this example is a little oversimplified. Simplified. And here's why. We didn't violate the continuity of x. We didn't suddenly teleport from one x value to the other. If we wanted to get from one x value to the other, we had to go over there. So x is continuous. That's okay. But we have these sudden weird jumps where you're going from one velocity to another without ever going through the velocities in between. And that's what we said before, right? If you want to go from this velocity to this velocity, you have to go through the velocities in between. In fact, we have a whole quantity, the whole point of which is to discuss changes in velocity. What's that quantity? Acceleration. So we're going to find, just to jump the gun a little bit, that if you take the slope of the velocity graph, you get acceleration, but here you can't take the slope of that. There's no slope to take. So v is not continuous, and that's where we run into issues, where this is oversimplified based on what we had already said. We had already said last couple lectures that x has to be continuous. You can't magically appear at a different x value without going through the values in between. B has to be continuous. A is okay for us to take jump cuts, but B it's not. Okay? So it's a good thing to get us started, but I do want to point out that it was a nice exercise to get us going, but it's oversimplified even for our purposes in this class. Okay. So the next example I'm going to do is not oversimplified, right? It's going to be basically right at the level of this class, and that'll be my next exercise, my next example. Are there any questions before I do that? Before I start that new example? All right, so let's do it. Now let me give you a little bit of a preview. Let me give you a little bit of a master graphing thing here. So x versus t, position versus time, velocity versus time, and acceleration versus time. Oops, x. Those are going to be the three things we look at, right? So those are the three main variables that we're going to graph. We're going to be interested in tracking the position, velocity, and acceleration as they evolve with time. If you want to go down this way, you take the slope. I just showed you that. I just showed you that if you take the slope of the x versus t graph, you'll get the velocity graph. We just went through that process. And, as I will show you in the next example, if you take the slope of the velocity graph, you can get the acceleration graph. It is also possible to work the whole thing in reverse. You can, from a graph, you can get the graph above it. The reverse process is called area under the curve. And I'll show you how to do that too. And so the most logical example that I can do here to be able to show you everything is to start with a velocity versus time graph. Because if I start in the middle, then I can first show you how to take the slope to get acceleration information, and then I can also show you how you can do this new process called area under the curve to get up here. So that's how you move between them. You might say, can you take the slope of the acceleration versus time graph? What's down here? Beyond the scope of our course. You might say, can you take the area under the curve of the top one and go up here somewhere? Yes, I don't think that would be useful at all. Also, not relevant anyway to the course. So we just move back and forth between these three. You move down by taking the slope, you move up by doing this process called area under the curve. Okay? So, let's go ahead and I'll put down a velocity graph. It doesn't really matter what it's shaped like. The point is that once we have it, do we know what it's saying? So let me go ahead and do that. And I'm going to be real lazy, because I'm going to pick the same exact shape. This is my velocity graph now. If you want, you can sketch it down again. But I do this, number one, because I'm apparently not very creative with the shapes of my graphs. And secondly, because I want to make an important point that the shape itself is not indicative of anything. Now that this is giving a velocity graph and not position graph, the motion is totally different. So if you wonder, for instance, why all your instructors are sticklers about what you're labeling, what you're plotting, it makes a huge difference. If you don't label your axes, your graph is basically useless. Okay? Let me sketch out what this new graph looks like. So if we read the information off of it, what is it telling us? So this graph says that at t equals 0, what's my velocity? 0. So I'm at rest. So at t equals 0, now it's telling me not that my position is 0, it's telling me that I'm stopped. Let me ask you this, where is it? Is it x equals 0? It doesn't say, right? This is giving me information about velocity. It doesn't tell me where I am. All right? Now, when 1 second has passed, it tells me now that my velocity is plus 3 meters per second. So my velocity now is plus 3 meters per second at t equals 1 second. Now, I know for sure that I went to the right. I do know that because my velocity was 0 to start with, and then it became positive. So I know I'm moving to the right, but I'm not being told at all where I am, right? I'm being told about what is my velocity, not what's my position now. Then, at 2 seconds, my velocity is plus 2. So where should I draw this now? Should I draw it to the left or to the right?
Right.
Still to the right. I'm still going to the right. I haven't turned around. At t equals 2 seconds, my velocity is plus 2 meters per second. I've slowed down, but if my velocity is still positive, then I'm still going to the right. So right there, notice the big difference, right? Before, that meant turning around. I didn't turn around. I just went to a smaller positive velocity. And remember before, this meant I stopped, right? Because I was at a constant position. But what does it mean now? I'm at a constant velocity, so I'm still going to the right over here at t equals 4 seconds, but I'm just doing it at the same velocity that I had at t equals 2 seconds. So very, very, very different, right? Even though the graph is the exact same shape, whether it's position or velocity that's being plotted on the vertical axis makes a huge difference. Okay? So that's again why myself and all your other instructors are sticklers about plotting what you're putting on the axis, what you're plotting. What is the quantity being plotted? What are its units? Because otherwise graphs are basically useless. Okay? So that is the information that is being directly given. Okay? It does not give me where I am at all. It just gives me information about what's my velocity at each time increment. So let's go ahead and talk about slope. So the slope of this graph is rise over run. Now the rise is how much my velocity is changing. And the run is still the time. So there you can see, what is that? What quantity is that?
Acceleration.
That's acceleration. So, like I claimed before, if you take the slope of a velocity versus time graph, you'll get acceleration. Well, this is where there's another reason why picking the same shape is handy, because I got these slopes before. This is my graph, but it's now acceleration. Meters per second squared. So that's my acceleration graph. My acceleration is +3, then -1, then 0. So this just allows me to expedite delivery of material to you. So we don't have to do the slopes again, right? We did the slopes. Now it's just the slopes have different meaning. The slope is now a velocity graph, so the slopes are the acceleration. So let's go ahead and throw those in here. So my velocity, of course, is always to the right here. I established that already. But let's write down my accelerations. My acceleration, which is constant, at +3 meters per second squared here. So what happens when the velocity and acceleration point the same way? You speed up. All right. Well, is that what happens during that time period? Yeah, that's exactly what happens. You start from rest and you speed up. The acceleration tells you have to add 3 meters per second for every second. Well, it lasted 1 second, so it had a chance to add exactly 3 meters per second. The acceleration during the second bit we found was -1 meter per second squared. So the velocity and acceleration point opposite. All right, so what happens when that occurs? You slow down. Did you slow down? Yeah. You started this time interval at 3 meters per second, then this removes 1 meter per second for every second that you give it. It had exactly 1 second, so it chipped away exactly 1. So you're now, instead of 3 meters per second, you're going 2 meters per second. Finally, the acceleration on the last leg is 0. So what happens when the acceleration is 0? Not stop. Constant speed. Is that what occurs? Yeah. So it's all working out very nicely. Okay? So everything that is the information that's being conveyed on the graphs, that is something that is reflected in when you bounce this out to the real world. If you were actually watching somebody undergo this motion, it would all kind of make sense. Now, our final order of business, we've started here. I've taken the slope again, gotten this, but now I want to show you the process of area under the curve. Okay? So, let me clear some space. Go back to my original graph, clean it up a little bit. You again might want to sketch it again if you want to keep your notes a little cleaner. So I want to go back to this graph, but now I'm going to get information out of it in a completely different way. I'm not going to take the slope. I'm going to do this process called area under the curve. So area under the curve, if you haven't seen this in math class, it's literally the area that is trapped between your graph and the horizontal axis. So when we say under, what we mean is between the graph and the horizontal axis. So let me mark off these areas. The area, of course, can be broken up into bits. This right here is the area under the curve during the first second. It's trapped between that line and the horizontal axis. I'll label this A. That's the area under the curve in the first second. Then, the area under the curve in the next second looks like that. Remember, you have to count up all of the things that are trapped between the graph and the horizontal axis. So this is the area under the curve in the 1 to 2 second time period. And then finally, we can talk about the area under the curve in the final 2 seconds. So it's trapped between that horizontal line and the horizontal axis. So, the area under the curve of a velocity versus time graph does not give position directly. It gives displacement. So if we can get area A, which is the area from 0 to 1 second, it'll give us the displacement. Displacement can easily be parlayed into information about position if you have the right ingredients, but it's not going to give you the position directly. Let me give you an example why. So let's say this velocity graph, okay? Someone is going to call you on the phone and tell you about their velocity. So they're essentially giving you their velocity graph. They call you up and say, hey, how's it going? So, guess what? My velocity is 0, then it's plus 3 after 1 second, then it's plus 2, and then I'm basically just telling you all about what's their velocity at what time. And then at the end of the phone call, they say, oh, by the way, where am I? Can you tell me where I am? You say, I have no idea where you are. Okay? You're calling me on the phone, giving me all this information about your velocity. How am I possibly supposed to know where you are? Right? How fast you're going has nothing to do with that, right? It's like someone calling you up, giving you their speedometer readings, and you're supposed to figure out from that where they are. And there's no way. There's missing information. It's like over here. We have no idea where this started. We can certainly say that they're moving to the right because the velocity information is plus, but we have no idea where to start. So there has to actually be one last extra piece of information given that's not on the graph, which is where did you start this velocity from? So then you can use this information. So for instance, if someone calls you on the phone and saying, hey, I'm on 280, this is where I'm starting, and now I'm driving this fast, now I'm driving this fast, and now I'm driving this fast, then you can figure out where they ended up. Okay? If you not only know what was their velocity information, but where did they start with that velocity. So area under the curve is only one thing that you need to do. You also need to be given what we call initial conditions. That's a separate piece of information that needs to be handed to you. So for instance, let's suppose in this case that you're given that x initial is 0. So that's something that the graph does not tell you. The graph tells you that your velocity starts at 0, but it doesn't tell you where you started. Okay? So now we're given that you start at x equals 0. Someone is nice enough to tell you that as well as the velocity information. So now, let's go ahead and find the area under the curve. The area of that curve, well, you can literally think of it as a triangle, right? For you guys, there's going to be basically triangles and rectangles and combinations, okay? So 1/2 base times height is the area of a triangle. So this is 1/2 times the base. How wide is that triangle? 1 what? 1 second. And what's the height of that triangle?
3 meters.
Plus 3 meters per second. So what does that come out to be? Well, first of all, the seconds cancel. That's reassuring. And that's about as much evidence as I can give you that this really does produce displacement. And then 3 times 1 times 1/2, that's plus 1.5 meters. So that tells me that because of the velocity information that you were handed, you ended up 1.5 meters to the right of where you started. It doesn't tell you where you started and where you ended, it just tells you how they differ. In fact, I'll throw that into the graph here. This is my displacement plus 1.5 meters. But if someone was nice enough to hand you separately that you started at the origin, if you went 1.5 meters to the right of that, what x value are you at? You're at 1.5 now. All right? So let's keep doing it. Doing this area under the curve process. Let me clear some room up. Guess I'll have to go over here. Oh, yeah, that wasn't the best thing to erase, but I guess I'll bring it back. Okay, so let's do area B. Area B is from 1 second to 2 seconds. So this is a little bit more complicated looking. But remember that you can always break it up into simpler shapes. So the area under the curve in part B is the triangle stacked on top of a rectangle. That's the most complicated thing I'm going to give you. It's going to be either triangle, a rectangle, or a triangle stacked on top of a rectangle. Question? No? Oh, okay. So let's work out 1/2 base times height for this one, and of course triangle is base times height. They have a common base, by the way. The common base is 1 second. Of course, that's because I'm restricting my calculation of the area under the curve to this 1 second. So that sets the side borders. The height here of the rectangle is what? 2 meters per second plus 2. And then, of course, this stacked on top of it, that's 1 meter per second. And I'll leave it to you to confirm that the area of those combined is plus 2.5 meters. So that's my displacement during this time interval. So based on the velocity information during this time interval, I've been able to conclude that the displacement is plus 2.5. So I'll go ahead and sketch that in here. That's displacement is plus 2.5 meters. And again, if you're wondering, okay, yeah, I see that the units work out to be meters, but is this really displacement? One of the exercises toward the end of homework number 2, I have you use the constant acceleration equations to verify these results. The beauty of these graphs, remember we need 3 things, right? The constant acceleration things, we need 3 things. These graphs always have 3 things. because you'll have the time, that's 1, and you have the initial and final velocity, so that's 3 total, right? So you use equation number 4. Equation number 4 is the one that has those 3 as the knowns. You can find whatever you want. Presumably you're looking for displacement here. So that hopefully will give you enough justification that this works. The only thing that you have to watch out for is if you're trying to apply the constant acceleration equations, there'd be a big error you could make. Let's say you try to find the displacement for the entire thing all at once, right? So let's say you want to say, I just want to know the displacement for the whole trip. So you take V initial is 0, V final is 2, time is 4, you plug it in, you'll get the wrong answer. Can anyone tell me why you would get the wrong answer for the displacement? What happens to the slopes here? Slope changes. What's the slope again? Acceleration. So if you have 3 different accelerations in the 4 seconds, you can't apply a constant acceleration equation over that entire trip. That's why they're called the constant acceleration equations. They only work if the acceleration is the same throughout your time interval. And there's 3 different accelerations here. You could apply the constant acceleration equations, but you would have to restrict yourself to each segment, right? Because each segment is its own constant acceleration that's different from the other segments. So be careful there. Okay? So we got the displacement for the second part. But what position are we at now? Are we at 2.5?
No.
4. You got to add up what you're doing. So don't forget that finding the area under the curve is not raw position information. It's displacement information. And displacement is something you do. But position is something you have to index from a common reference point all the time. So if we start at x equals 0, and we go 1.5 meters to the right, and then we displace 2.5 meters to the right, well, we are not 2.5 meters from the beginning anymore. We're 4 meters away, right? Does that make sense? Okay, so let's finish this off. Do segment C. Well, segment C is the easiest. It's just a rectangle. So the base is how wide?
2.
2 seconds. And what's the height of it?
2.
Plus 2 meters per second. So base times height? 4 meters. Here, base times height is like rate times time, right? So you can kind of see there pretty straightforwardly, right? If you go 2 meters per second for 2 seconds, well, you multiply the 2 together, you'll get how far you went. So that's my displacement for the last bit, from here to here. So displacement is something that I did. Displacement describes what happened in the last 2 seconds. But my final position is not 4. What is it? 8. So again, I want to emphasize here, if you take the area under the curve in any given segment, you'll find the displacement during that segment. So the raw area under the curve was plus 1.5, plus 2.5, and plus 4. Then we parlayed that into position information by being separately told that the position is 0 to start with, and then stacking those displacements on top of each other so that we have positions were 1.5, 4, and 8. Okay? So don't forget that. Don't forget to stack your displacements if you want to index position. Are there any questions on that? So you can see there's a tremendous amount of information here, right? We're just given the velocity graph and this extra little bit of information about where we started. We could reproduce where we were at all times and what acceleration we had, right? We were able to get to all this information back, okay? So one graph can carry a tremendous amount of information. I guess, I know I erased the graphs, so let me sketch them back up here for a second. So the 3 graphs again were position, velocity, and acceleration versus time. So moving down, taking the slope, that's no problem. But for taking area under the curve, if you want to get from velocity information to position information, you need to take the area under the curve, and you need initial position information. Likewise, if you want to move from acceleration to velocity by taking area under the curve. So someone's calling you up on the phone, and they're giving you this amazing acceleration information. It's the best acceleration information you've ever heard. Okay? Now I'm going plus 1 meter per second squared. Now I'm going plus 2 meters per second squared. They're telling you how much they're adding to their velocity at all times. Right? Now I'm going to add plus 7 meters per second in the next second. Now I'm going to add plus 2 meters per second in the next second. And then at the end of the call, they say, now how fast am I going? You say, I have no idea. You gave me all this fancy information about what you were going to do to the velocity, but you didn't tell me what velocity you started with, so you can't figure out what value you started changing from. So likewise, if you want to get area under the curve here, that's just going to give you your delta V, right? So just like here, if you want to convert from delta x to x, here, if you take area under the curve, that gives you just delta V. And you also need information about what was your initial velocity that you started accelerating from. So that's a common thread. Is you take the area under the curve, you'll just get the change in something, but then you need initial condition information to convert it to the graph above. So just like area under the curve here just gave us delta x, and we needed initial position to convert it into position information. Here, when you take the area under the curve, it just gives you changes in velocity. The initial velocity as well needs to be separately supplied so that you can try to parlay it into velocity information. So our final order of business is to make a graph. Make a graph of the position versus time. So this will be the trickiest graph that you see. It's the most complicated thing that you're going to see because it's the only one that can be curved. Let me show you. Let's see, where do I have room for it? I guess I'll have to clear out what I just put. Now I guess I'm going to have to clear this out, unfortunately. It's the only place I have enough room. We're going to have to refer back to it. So let's go ahead, sketch the position versus time graph. Make it a little bit bigger. It's going to be a little bit more featured than some of the other ones. So we have 4 seconds that we need to account for on this axis. But we have to, and then the x values, those are all positive. But we have to make room for what's the largest x value that we would have to plot? 8. So we're going to have to make room for 8. So let's try to do 8 evenly spaced tick marks. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8. And other ones that I might label are 1, 2, and 4. I think those will be the ones that are mostly of concern. And let's go ahead and sketch in the positions that we know. We know that at t equals 0, what's our x value? What's that?
0.
0. That was given, right? At t equals 0, we're at the origin. But after 1 second, where are we? 1.5. So, right about there. Plus 1.5 is, of course, halfway between the 1 and 2 tick mark. After 2 seconds, where are we? 4. So one of the things that can really go wrong to begin with here is that you start accidentally plotting the displacement values and not the positions, right? So we didn't plot 2.5 here. We plotted 4, right? Make sure you understand that. And then at the end, what's our position? At 4 seconds? 8. So we'll draw that. So can I just connect the dots and go home? That's the leading question. I can't. Okay? So how do you connect them? Well, first of all, if you try to connect them with a straight line, you would find that they don't fit anyway. But remember, the process that we got was area under the curve to get this. And to head check us, we have to make sure that the slopes of this are this, right? So the slopes of this graph are the values on this graph. Well, we have the values here, so we can get the slopes here. Remember, our graph handed us the velocities, so here they're the slopes. So the velocity was 0. So that's, I'm going to draw myself a little flat part there, because there the slope is 0. So that not only has a value of 0, it has a slope of 0 meters per second. Then, at 1 second, my velocity was plus 3. So my slope here should be plus 3. So this is kind of giving me a way to connect the dots, knowing how they should connect. Because at these points, I not only know where I am, I know what my velocity is, and that's the slope. Now, I'm just estimating that. I know it's a positive slope, so I'm just estimating it. And then the next value, that's plus 2 meters per second, so the slope is plus 2, so I draw that a little less steep, right? So maybe something like this. And then the slope is still that later on. The entire last 2 seconds, the velocity doesn't change, so here the slope doesn't change. In fact, that's the easiest one. I'll do that right now. The slope during the entire last 2 seconds is plus 2 meters per second. That's because the velocity is constant, so the slope here has to be constant. As you progress through your time, you're going to evenly add position on the vertical axis. That's what a constant slope would indicate. So this is a constant velocity. So a constant velocity is a constant slope on this graph. But here's where the curve comes in, right? Because if your velocity is changing, then you do not cover position evenly with time. If your velocity is changing, then the slope here is changing. Well, I have a nice little road map of that. My slope will increase like this. It'll curve. So I don't cover my position evenly with time. At the beginning, as time passes, I barely increase my value. That's because I'm going real slow. Then it gets steeper, which means that as I go stepping along in time, I cover a lot more distance, right? So getting steeper means that I'm going faster. I'm covering more x. I'm covering more position here as time progresses, okay? So I'm going faster. Then, on this part, I curve the other way. I'm slowing down. So I went as fast as I'm ever going to go, which means the slope is the steepest, and then I decided to back it off a little bit and curve back over. So here I speed up, so that's why it curves the way it does. Here I slow down, so that's why it curves. So when you are accelerating, the position versus time graph can be curved. Okay? Now that you could not take the area under the curve of, but again, you don't have to because you're already at the top of the thing, so taking the area of the curve is not going to produce anything useful. So that's the most complicated that you'll see. You will generally see that this can be curved at the most complicated, this will be linear, and then these will be flat because, of course, acceleration for us is going to be constant. Okay, so that's the topic of graphing, and it also closes out your homework number 2. We'll pick up new stuff on Monday.